Thank you, Ethan. And I really want to give a deep appreciation for the wonderful opportunity I've had to be here today and yesterday too. It's been a really stimulating and exhilarating day for me, and I really have appreciated the opportunity to come here. So thanks a lot for the invitation. So there we are. What I want to do today is talk to you a little bit about our work on carbon capture. Some of you thought I was going to talk about carbon dioxide conversion. I am not. I'm going to focus just on the capture side of the CO2. You can do whatever you want with the CO2 once we've captured it, either convert it or bury it underground or whatever. I think it was mentioned that we have to be concerned about the sustainability of our current way of life and the fact that we are seeing significant impacts of climate change around the globe, actually. And so this is something that really needs to be taken concerned about. And the reason for this has been attributed to global warming. If we look over here, in the last 5 decades or so, the temperature's gone up relative to what it was in the pre-industrial revolution days by about, actually right now it's about 1.5 degrees, which was considered the threshold trigger in the past, but it seemed like we are not going to be able to sustain and keep the temperatures below 1.5 degrees increase in the environment. And the reason for this can be attributed directly to the actual cumulative CO2 emissions since the dawn of the industrial age. So if we look here, this is the cumulative CO2 emissions, and this is the temperature rise. You can see a very strong direct correlation. And if we continue as usual, we're going to see a temperature rise by the mid-century of around about 2.5 degrees Celsius, which is going to be unsustainable. And so what we really need to do is find ways of mitigating these CO2 emissions and ensuring that we actually limit them to a certain level so we can keep the temperature rise to about 1.5 or 2 degrees by the mid-century if we can. Now, where do these CO2 emissions come from? Well, there's about 35 gigatons per year from the fossil fuels and industrial sources. There's another 4 gigatons per year from land use change in the system, and that totals about almost 40 gigatons per year of CO2 that's emitted to the environment. Now, this doesn't all stay there. We do have land sink terrestrial sources that absorb the CO2, vegetation and the like, that absorb the CO2, but we also have a significant amount of CO2 that's absorbed by the oceans as well. About a quarter of the CO2 that's emitted gets absorbed by the oceans, which means that we have sinks of about 22 gigatons per year in the system. But that does leave us with a whopping about 20 gigatons per year that accumulate in the atmosphere each year. And so that is quite significant, leading to a rapid rise in the overall accumulation of CO2 in the environment. Now, how does this impact us? Well, if we think about the greenhouse gas emissions, this is CO2 equivalent. If we go business as usual, we're going to see by the turn of the century, we're going to have a temperature rise of around about 4 degrees or even larger, which is really going to be unsustainable. So it means that we need to do something now to start mitigating this CO2 emissions. And what we really would like to do this, if we model it right, is start right away and actually start limiting the greenhouse gas emissions in the environment. And if you want to keep the temperature rise to be below 2 degrees Celsius by the turn of the century, we are going to have to follow this kind of a path, which means we've got a very large area of CO2 emissions or greenhouse gas emissions we need to mitigate. And somehow we've got to sort of avoid these kinds of emissions accumulating in the environment. Which means we should transition to non-carbon sources, nuclear, renewable energy, etc., etc. So that would be one of the goals. Of course, we're not going to be able to do everything like that, and we are going to have to rely on carbon capture, utilization, and storage, both from stationary emissions, and we need net removal technologies with permanent storage. In other words, what do we do with the CO2 once we've caught it? And we'll talk a little bit about that. But there are some unavoidable greenhouse gas emissions from cows burping, for instance, from vehicles, for airplanes, and so on. And we cannot mitigate these emissions at all using normal circumstances. So we have to think about how do we do that. We take out CO2 from the environment. So we need a net negative greenhouse gas emission. So instead of actually emitting CO2, we need to start taking it out of the environment. And so we've got that particular scenario there. But because of these unavoidable greenhouse gas emissions, we are going to have to think about doing it even earlier than that and start by the next decade or so, having a very large amount of CO2 taken out of the environment itself. So the net emissions should be negative. And so we've got to think about direct air and ocean capture, removing the CO2 from the air, removing CO2 from the oceans, and other techniques as well. But those are some of the actual important components of this. Now, if we look at what the concentrations are, we can see what a formidable problem it could be. Point source capture, if we actually, the point at source at which it's actually produced, is around about between 2 and 20% CO2, depending on whether you get natural gas fired or cement industries or what kind of emissions that you are getting, which are really high concentrations, so it's quite easy in principle to separate CO2. But we realized we have to start taking CO2 out of the environment. We have to start taking it out of the air, where it's around about 0.042% CO2. Very, very dilute. And of course, this poses a much more significant challenge to the overall separations. And then we've got direct ocean capture. We've got the actual dissolved inorganic carbon in the form of bicarbonates and carbonates on the order of about 2 millimolar in there, which actually, if you look at it, it's around about 140 times more concentrated volumetrically in the oceans than it is in the air. So there could be some incentives to go after the CO2 that's in the oceans as well. And if I've got time later on, I'll talk about that. I don't think I'll be able to cover our work on that stuff. So let's just think about how do we go about capturing the CO2. Well, traditionally, there are various sorption modes for CO2 capture and release, which we do is CO2 with some kind of a base which form a complex as shown here. And what we've got to do then is, how do we actually do this? We can either do it by absorption type processes or adsorption type processes. Both of them rely on the interaction on this kind of a chemical reaction, and then when you fully loaded the sorbent, fully loaded here, what we have to do is take it to a desorber or take it offline and heat that up there so we can break this chemical bond and reverse the chemical bond. And what you've got is then is a dilute gas stream coming in here, and we release the CO2 in a concentrated, hopefully pure form at this end. So we've done a very strong concentration process. Now this is all very good. These kind of things are a little difficult for direct air capture, so using some of the sorbents that people are using. So how do we do this? Well, there are a number of different sorbents that people have used for this. This shows some of the liquid adsorbents and solid adsorbent type systems. And you can see from here the temperature ranges over which they operate would be on the order of ambient to about 200 degrees Celsius. In general. And the strength of interaction is going to be important because this tells you how strongly that bond is and how much energy we've got to put in there to break that bond and reverse this reaction. Now the problem with this is all of these require some kind of temperature swings. They all require temperature swings of 50 to 100 degrees to reverse this chemical reaction, which means you need to have some thermal sources. You also need to worry about heat integration so you can recover the heat and go through the cycle heating and cooling. You had to worry about sorbent degradation, particularly at the higher temperatures at which you're operating during the desorption side. And you also have to think about you heating up the solvents, you're heating up the support, you're heating up everything. So that could also lead to inefficiencies in your overall processes. So what we're interested in are there ways in which we can use isothermal kind of conditions and the ambient conditions and avoid having to go through all these heat and cooling type cycles and the like. And this is when we started thinking about using redox electrochemical processes for CO2 removal. This is the capture and release of CO2 is regulated by the oxidation state of some redox active species. And it's under applied potential. So if we change the potential, we change the redox state, and therefore we change its capture and release of CO2. And we can think about it being governed by the Nernst equation, which we will define here. So basically what we're talking about there is taking some component here, Q, and reducing it by adding electrons to it to get this activated or reduced compound. And that is governed by the Nernst equation. This gives you the reduced compound over the oxidized state is related to the actual applied potential relative to the standard state potential for that redox reaction as shown here. And if you look at the fraction of the total quinone or total sorbent that's actually being activated, we get a curve that looks like this, something like this. So this is the reduced or activated fraction of the compound. And so if we go sufficiently negative potentials relative to E naught, what we find is we get this kind of absorption. We get the reduction of this carrier of this component, and it reacts with CO2 to give us this kind of a complex. And that's great, that's for absorption. If we want to desorb it now, what we want to do is release the CO2 as a concentrated solution. We can go through the reverse process and oxidize it, go over more oxidating potential over here, and we can reverse that reaction and get CO2 coming off. So we can absorb CO2 at low concentrations here and desorb it at ideally 100%. So what we've got then is a process in which the energy is going to be targeted to the sorbent molecules only. We're only targeting the energy to this particular molecule. We're not targeting the whole solution, anything like that. Now these processes can be modular. They can be rather compact. They can be isothermal, which is a big point. They can be plug and play. As long as you've got a big enough outlet, you can plug and play these things. And they can also be driven by renewable or at least non-carbon type energy sources. So they have a lot of typical potential advantages in these cases. So how do we go about doing this? There are a number of different ways we can actually think about doing this. And the first is a direct approach. And we can think of having some compound. I've gone from Q to A now. This is A. And we can reduce it. When we reduce it, we activate it. When it's activated, it can then react with the CO2 to form this complex, right? And then what we want to do, we want to when we want to release the CO2, we have an oxidation process, remove it. It no longer has affinity for CO2, so the CO2 comes off in a pure stream. That's basically what we've been talking about. And one example of this would be looking at quinone type molecules as shown here. This is a naphthoquinone, and what we can do is take that on reduction at a cathode and in touch with a CO2 stream, we can capture the CO2 in some kind of a carboxylated form like this, and that we'd capture the CO2. We can then take it to the anode side and oxidize again, and when it's oxidized, it no longer has capacity for the CO2, affinity for the CO2 can then be drawn off. That's the one approach. That's the most direct approach. The second approach is a semi-direct approach, in which we go through this. Again, you've got this activated compound. When we activate it, it doesn't actually get activated like this. What happens was, when we reduce it in an aqueous phase, there will be a water molecule, you'll get it in a reduced phase, it becomes protonated. So this is a proton in there, and this hydroxyl ion. Now this hydroxyl ion, it means the pH goes up, which means that you've got a very alkaline solution, and you've got the CO2 then being absorbed, and it gets absorbed as a carbonate or the bicarbonate in the solution. And when you go through the oxidation process again, you deprotonate this molecule, the pH goes down, and therefore the CO2 gets released as a CO2 rather than still being in the carbonate or bicarbonate stage. And one example of this, again, you can look at quinone type molecules, is when we do the reduction, it reduces and it also becomes protonated, and therefore the CO2 gets picked up at the high pH as a bicarbonate ion. And then you can go through the reverse process and so on. And then the last one is an indirect process that I will talk about in a moment or two, so I'm not going to go over this particular thing. And this is looking at what we call electrochemically mediated amine regeneration. I'm not sure I need to really talk about the energetics. I don't have time to really talk about it, but we can certainly go through the energetic analysis. We can do very detailed thermodynamic calculations and arrive at what the overall the potential is as a function of the state of charge or the amount of charge that's been transferred. And we can go through the adsorption and then the absorption and desorption and activation, deactivation side. And the important part is the area under that gives you the overall, the minimum energy. So we can actually calculate what the minimum energetics would be for any particular kind of a process. We also have to worry about the fact that there are overpotentials, so we need for finite rates, ohmic resistances, reaction kinetics, transport factors. All these come into play that make it less efficient than the ideal case. And ideally, you'd probably have some kind of an applied potential applied voltage across the electrodes, something like this. We get some at delta V, and so what we get then is the actual work would be given by the amount of charge transfer times delta V, divided by some kind of a factor here, A to F, which is your electron efficiency. So you can see that basically the Faradaic or Coulombic efficiency or electron utilization is given by the number of molecules of CO2 that are captured per electron that's transferred. And that's an important component. I'll come back right at the end of the talk to say how we can actually really optimize this and increase this quite dramatically over what other people have done in the past. So the important part is that the lower the energy efficiency or the lower your electron utilization, the more inefficient your process is, your work goes up. So that's really what I want to say there. So let's talk about this other case here. What we've got is a situation in which we, maybe I'll just go through this reaction process here. We have an absorption column. Instead of having a thermal stripper here, we have an electrochemical cell. This electrochemical cell, in this particular case, has copper electrodes on it. So you've got two copper electrodes for the anode and the cathode chamber, and this is separated by some kind of a membrane, an anion exchange membrane separating the two cells. What we'll have is in the absorption column, we have flue gas coming in, we pick up the CO2 and it reacts with an amine to form the so-called carbamate. We then take this solution, the carbamate solution, and feed it to the anode chamber of the electrochemical cell. In the anode chamber, what happens is that we are releasing copper ion. And this copper has a very strong affinity for the amines. The amines have a very strong affinity for the copper, and much stronger than it has for the CO2. So the CO2 gets displaced. The copper displaces the CO2, and you can then basically, and here you've got this particular reaction occurring, and you can then take it to a flash tank where the CO2 can then be taken off and compressed to do whatever you want. This particular amine copper complex now is of no use to us at this point, so we take it to a cathode chamber where we reverse the reaction, we plate out the copper, and we regenerate the amine, and the amine can then be sent back to the absorption column. This can all be done isothermally. It can be done rather efficiently. We can operate at different pressures. The actual voltages we need are around about 0.5 volts per cell, which is quite low. Which means the energetics are quite favorable for this particular system. This will show you the kind of system that we've worked on. This is about the size, 10 centimeters by 23 centimeters in size. I'm not going to go into detail, but this shows you the actual, the structure of these cells. And the whole equipment, and it's a process diagram for this, and that's the whole equipment that we've actually had. Should I say we had? It's been cannibalized by other groups, other students in the group, but we are trying to rebuild it. So just to give you an idea how this actually works, what we've got then is an applied current of, say, this particular case is about 0.5 amp in one direction, and when you get the cell potential going up. What you find is that we are actually releasing CO2 in this particular case. What happens is that as we continue on here, of course, what we're doing is we are degrading the anode is dissolving, the cathode is growing. At some point, you're going to run into problems. So we have to switch the flows around back and forth. We switch the flows, we also switch the currents, and so on. So, but over the 100 hours of operation is operating very stably, and we're getting really good gas output, and the gas purity is pretty high. It's close to 100% overall. And you can see after 100 hours that these electrodes are still looking very, very healthy, which is really important. Now the question is, how useful is this? Well, if you use that thermodynamic model I talked about, which we didn't really describe, we can actually do a fairly detailed analysis. We've done a complete TEA, technical economic analysis of this, but this gives you the actual work, and the work is in kilojoules per mole of CO2. That's one of the important things. So if you look at the typical, the standard kind of processes we have with amine type systems, you'll get on the order of about 50 to 60 kilojoules per mole. This is a special case, so I won't go into details about that. With our particular process, we get about 50 kilojoules per mole, so we can see that it's actually quite competitive with the standard process. And what's driving a lot of this is this overpotential here that we need to do. This is the minimum work. This is the overpotential that's required, the work that's required to overcome the overpotentials. And so basically that's something we need to work on as well. You've got to worry about bubble management, bubbles that form in the cathode, in the anode chamber as you're releasing CO2. We have to worry about flow to cell design and things like that. And we know how to do some of this. We don't know how to do it all yet, but we are working towards that. And one of the things we found just by adding surfactant to the system, small concentrations of surfactant to the system, we managed to operate quite well. This is what happened here. We got some particles coming out of the anode chamber, which is unusual. I won't go into details about that right now. But by adding a small amount of surfactant, I just want to point out that just by changing the solutions a little bit, we can see we get a very nice clear solution coming out of the anode chamber. Here we've got the sorbent, and there we've got the CO2 that's been released, and so on. And by doing this, we can see that the actual cell potential can go down from about 0.55 down to about 0.4, which means the overall energetics for that particular component goes from about 40 kilojoules per mole down to about 27. So we get a very significant increase in overall efficiency of this process by doing that, which makes it even more competitive with the normal operations. But that's just one general area we work in, and we could go into a lot more detail about this. I just wanted to give you a flavor of some of the work that can be done using electrochemical as opposed to thermal processes. Another approach is a direct system, and this is what we talked about before when you got a quinone and it's reduced and we get the carboxylates forming, and then you can release the CO2 on oxidation again. Question is, where did these electrons come from? Well, we've coupled this with another system with the ferrocene. When you get ferrocenes, basically when they oxidize, you get your ferrocenium, these electrons can then be used to drive this overall separation operation there. And so what we've done is we've taken hollow carbon nanotubes, and we've taken polymerized ferrocene in this case, wrapped them around the nanotubes, dispersed them on top of a electrode substrate, and we get a film like this. You can see in here the nanotubes, and these are all coated now with ferrocene. We can do the same with the quinones. That we can do that. And then we assemble them into some kind of a sandwich as shown here, where we have a quinone electrode, immobilized quinones, we have a ferrocene electrode, and then we have some spacer in between the two, just to allow for ionic conductivity. These are then wetted with some kind of ionic liquid electrolyte. We use ionic liquids because they provide good conductivity, but they also are non-volatile, which is an important consideration. We then assemble them as shown in this case, and when we apply a reducing current to this, we actually activate the absorption system and we capture the CO2. At the same time, of course, we've got the ferrocene going this way. When we've got the fully loaded, we can go back and do the sweep stream. We can reverse the polarity. On reversal of the polarity, we then release the CO2 as a sweep stream. So this is a typical swing type process, except instead of using thermal or pressure swing absorption, we're using electrical swing in these processes. I want to point out we started a company about 4 years ago. We formed a company, Verdox, which has been quite successful in raising funding, and it actually won the X Prize Carbon Removal Award last year. I think it was last year. No, 2 years ago now. God, time is flying quickly. So it does show this kind of technology has some merit. But how does it work? Well, this is one particular case when you pack the beds with the electrochemical cells, as shown here, and we feed it a CO2-rich feed to a bed of these systems. And what happened is, of course, the CO2 has been removed. So basically, the outlet gas here has no CO2 in it until such time as you saturate the bed, and it can no longer hold any gas. And that's what's happening here, for instance. They're coming on and on. This is just the time relative to the residence time. And after a period of time, we begin to saturate the bed, and we then get a breakthrough curve as shown here. But this indicates that this kind of a process does have merit, and it works reasonably well in this particular case. These are some early results. But we wanted to go beyond this and build up a stacks of these systems in which we actually have a bunch of electrochemical cells as this, and they're separated by conductive mesh fibers through which the gas flows, and by applying a voltage across the whole system, that voltage can then be divided across each of these cells, and we can then basically, we don't have to address each of the cells individually, we can just address the whole stack. But there are challenges, capacity, stability, and transport limitations. Because what we're doing is we're flowing the gas across here, and the CO2 has then diffused into these electrodes, which are now saturated with the ionic liquid. So there's some diffusional limitations and things like that. But what we've done lately is we've taken, we would flow through electrodes instead. And in this particular case, we've taken a melamine foam and coated with some kind of a gel. A polyvinyl alcohol network, we cross-link it and so on, and we coat it with the gel. We then put in carbon nanotubes and the polyvinyl anthroquinone. That's the quinone we're using, and so we get a shell, a system that looks something like this. The CO2 there, or the flow gas can flow through there. This whole thing can be activated, and we can then capture CO2 and release CO2 depending on the applied potential in the system. This just gives you an idea of what it looks like. This is the basic, the typical structure of the pure foam. And when you coat it with PVA, and then we've got the total porous electrodes in this case. When we wet it so it's not totally saturated with ionic liquid, but the ionic liquid actually wets the gel part of it around the actual fibers on the melamine foam. And so this is basically the overall structure. So we can now use this and pass the CO2 through it, as shown here. This is the one I want to show you. This is under high relativity, humidity, which is really good. What we've done here, let me explain this particular graph here. This is the CO2 being fed in at around about, what's the feed? Around about there, around about 400 parts per million, right? It's been fed in here, about 400 parts per million. We turn on the absorption. We can see we absorb everything. Nothing's coming out at that time. We then turn it off, and we release CO2 into that stream. Now, we're not actually releasing pure CO2 at this moment. We're just showing that we can do the capture and release. And we can do this, and you can see each of these basically right here. We're getting very good repetition. The Faradaic efficiency I told you about, that's really an important consideration, is on the order of about 85 to 95% in this particular case. So it's showing that it really works quite effectively. But, there's always a but. Now, what happens if we do it in the presence of oxygen? I was doing that with no oxygen present. We were cheating a little, because we're obviously going to have a lot of oxygen present in our systems. So what happens when you actually have to do it in the presence of oxygen? This is we apply a voltage of minus 1.5 volts. And we can see that it degrades over time. This is the CO2 concentration. The amount of CO2 that's actually captured is degrading over time in this particular case. Okay, so maybe we apply too large a voltage. Let's try something smaller. And so we do that again. And certainly we don't get quite as rapid a degradation, but we still get a good degradation in performance over here. And our overall capture capacity has gone down as well. Well, let's go down even smaller though and see what happens. If we go to minus 1 volt, we find that we do not get any degradation in capacity. It works very well in this particular, well, reasonably well in this particular case. And we don't get any degradation in capacity, although the capacity is really small, so it's unacceptably low. And the question, why is this? Is there any way we can overcome this? Well, the problem we have with these types of systems is these quinone type molecules is, well, I'll describe a little bit about what we've got here. This is the current and the potential versus ferrocene. What we do is sweep over here, and when we get to reduction potential, we actually move in this direction. We get the reduction potential, we get a current flow. It could be reducing the compound. And then we get a second reduction potential in this particular case. What's happening is that this quinone is going through a one electron reduction to form the semiquinone as shown here at that potential. And then we've got to go to a higher potential now because we've got to sort of work a little bit harder to get the second electron into that ring, and therefore we get the second system here, right? So that's basically what's happening. We're going through one electron reduction, then a second electron reduction occurs at a much more negative, much more energetic state. So with the presence of CO2 though, things change a little bit. Because what's happening is that you actually get that these two peaks seem to sort of meld into one, sort of, as shown in this particular case, in the presence of CO2. And that could be for one reason, that the quinones respond and react to CO2. So the proposed mechanism is that what we get is, this is the one I think is really happening in this particular case, is we get the semiquinone forming, and when it forms, it basically, it captures the CO2, as shown here. That changes electronic distribution in this case. It moves the electrons out, which makes it a lot easier to get that second electron into that system. And we then get the second reduction occurring at the first potential. And we then get that, so we got this charged compound that can now absorb the second CO2. And that's the one way. There's another way we can do it in which we have to go through the double reduction first before we can begin to absorb the CO2. And there are a lot of details I can go into. I won't go into details here. But the important part about this, if we look at those potentials where they are, and we look at the oxygen reduction potential, you have to worry about the fact we have oxygen in the system. Remember, we had oxygen in the system before, and then suddenly our performance started degrading. And that is because we have these, this oxygen reduction potential is about the same potential that we had for the original, for the actual CO2 capture, which means there are some issues here associated with that. And so we've got to think about what the problem is. Well, oxygen reduced redox active species. The oxygen can actually, at those potentials, can actually reduce our active species back to the oxidized form, and therefore no longer has capacity for CO2. And that a number of things can happen there. We can also get direct reduction of the oxygen to form the superoxide, so we're stealing electrons from the overall quinones. Or we can have reduced current efficiency because of other kinds of processes occurring in the system. There can be chemical degradation of redox active species as well. But let's take a quick look at what we've got in this particular case. So if you look at a whole bunch of these different quinones, and you've got, remember, we've got one reduction potential there, the other reduction potential there under nitrogen, and we've got the single potential under oxygen, under CO2 conditions. And you see the whole bunch of these different quinones we look at. Some of them, these are for the nitrogen cases. These ones have the single reduction potential in the presence of CO2, as shown here. These ones don't. And it depends on whether electron withdrawing, electron donating groups on the quinones type things. But the important part is the one I showed you. Well, those are the ones that are now of interest to us. The one I showed you, the anthroquinone, you see that the anthroquinone itself is actually on the negative side of the oxygen reduction potential. And that is why we're having problems with this, because basically we prefer to reduce the oxygen than the quinone in general. Okay, so that's something we need to think about. And the question is, how can we address that? Well, just recently we've done some looking at another one, this benzodiazepine quinone molecule is shown here. And what we found in the presence of oxygen, that we got the absorption and desorption cases. So here, we don't have any issues, or very little in the way of issues in this particular case. But with the anthroquinone, which is what we were looking at earlier, you see we get a fairly rapid degradation in performance in this system. So that really gives us an indication that maybe we are on the right track in thinking that we need to think about having quinones that are more positive of the oxygen reduction potential in this particular case. So if we look at that, this is what we find with this benzodiazepine quinone molecule. We don't get any degradation in performance, and we get electron utilization a little lower than we'd like, but that's okay for now. We won't worry about that. But the important part is, this is the green line is where we are for the benzodiazepine molecule, rid of the anthroquinone, which is on the left side here. So this explains a little bit of why we are in a better position with this particular compound for overall stability of these systems. And so that, good. Also, I did want to point out that we've got the issue that we've got the work depends reversely on this electron utilization, which is going to be an issue I want to talk about shortly. But let's just talk about the same. Those are direct cases when you actually the quinones actually react with the CO2. The other case we talked about is when we actually get the molecule itself becomes protonated, releasing hydroxyl ions that can then react to the CO2 to form the carbonate or the bicarbonate molecules. So in this particular case, we're using a common neutral red dye. as called, the phenazine molecule. When we go through the reduction, we're adding 2 electrons, there's 2 waters in there. What we find is we then protonate the nitrogens here, amines there, we protonate those, and in so doing we release 2 hydroxyl ions. We now challenge this with CO2. If you get CO2 being introduced, this CO2 reacts with the hydroxyl ions to give you the bicarbonate. So we're now extracting capturing the CO2 in the system. And you've got this kind of a process. The pH is there 12. Because you're doing this operation here, we are reducing the alkalinity. The pH goes down to about 7.1. We can then take this and reverse the process when we take off the 2 electrons, we get water, and we can then release the CO2 in the system. And so basically what we've got is this particular type of situation. I'll show you how it actually works quite well, actually, even in the presence of oxygen. We can have a flow system as shown here. What we have is let's start in this case. We've got the neutral red dye. We then take it to the cathode chamber where we reduce it. We get the protonated, for what's called the protonated neutral red dye, which means that the pH goes way up. We take the high pH solution and feed it into this chamber here where we contact it with the CO2 rich air. Once you've got that done, of course, hopefully we've absorbed the CO2 and the air leaving there CO2 lean. We can then take that stream and take it to the anode chamber where we go through the oxidation process. And when you oxidize this, the pH goes down and we sort of releasing CO2 as just CO2, no longer in the bicarb form. And that can then be released in the flash tank. So this can be done continuously. This is not the best configuration, of course, for a real operation, but it gives you an indication of how the concept works. And if we look at this, we're challenging with 15% CO2. This is over time, how much CO2 we've released at a time, and there's a cumulative amount of CO2 released. You see that we get a fairly steady concentration, fairly steady release of the CO2 over about 12 hours. But that's not as much interest to us as looking at direct air capture. And that's something we're really interested in looking at direct air capture processes, where the CO2 released now, we're challenging this with ambient air from the lab environment. So this is for 420 parts per million of CO2. This is over 96 hours, continual operation, and you can see we are removing CO2 at quite a reasonable rate. Not much different from what we had with 15% in terms of, and that's just because we have the way the contact is set up. But the important part is that we are able to do this for well over 96 hours under presence of oxygen with no degradation in performance, and this is good. We are now working on ways in which we can enhance the overall capacity of these systems by modifying that neutral red dye, and there's some significant other factors we can have. But that is an important issue here, is in all these cases, the number of CO2 molecules released per electron is always less than 1. So we don't get a very high electron efficiency. And if we can boost that electron efficiency, we can then enhance the overall energetics for the system. And so that's what I want to talk about right now. And the basic is to using a hemi-labile ion complex in this particular case, and you've got the various ligands here. When you do the reduction, you kind of free up the ligands, as shown in this particular case, and we then become susceptible to the CO2, and they can be captured the CO2 like this. And then when you go through the reduction, the oxidation again, you can release the CO2. In this particular case, we can actually think of the electron utilization. For 1 electron, we may get larger than more than one CO2 captured in the system. That's the basic principle of this idea. So what we've done is taken this particular compound, and you can see it's in the F3 plus oxidized state in this particular case. We then go through the reduction, and we end up with this particular, it's reduced now, but it's still in this particular configuration. What happens is these particular ligand groups here, they get released, and we get this particular formation forming. So they open up, and they get protonated. Those phenyl groups get protonated, as shown there. So that's great. we've shown now that what we've got is with one electron, we've now released 2 hydroxyl ions in principle. Right? So that's, I think, an important consideration. Now, one problem. Well, I think it's a problem. This is a catalyst for CO2 reduction. And we do see a little bit of CO2 reduction. Now, I know it's going to be heritage to say this, but we don't want CO2 reduction. We don't want to do that. The number of reasons is that our goal is to reduce this pure CO2 stream for subsurface sequestration. Most of the CO2 that's going to be captured is going to have to be buried in underground geologic formations. There's no ways we can get around that. Okay? So we want to make sure that we get CO2 that's actually pure. And if the CO2 reduction will lower the electron efficiency for CO2 capture, because some of the electrons are going to forming the CO. But also reduces the purity of the final CO2 product, because you now have a mixture of CO2 and CO, or whatever else your reduction product is. So we want to avoid that. And the way we do that is by adding a blocker, nicotinamide, as here, and it will sort of interact and block the CO2 from actually approaching the ion complex there, and therefore we can then rely on this CO2 being captured as just the bicarbonate and not being converted. So we can go through then, we go through the oxidation state again, and we go through the whole reverse process and release the CO2 and go back again to what we had before. So this is really what the whole the concept is, and the question is, does it work? Obviously, we wouldn't be talking about if it didn't. This is really what we've got, is we're looking at, again, a cyclic type operation, just cycling the current actually between 2 different values, and you can see how the potential varies as we go back and forth on this. We're absorbing CO2, desorbing CO2, and so on. And the amount of CO2 we capture in millimoles in each cycle is shown here as we pass through these cycles, and you can see that basically we are capturing and releasing at the constant rate in the system. The important part is that electron utilization now is not much greater than 1. It's about 1.43 in this particular case, and say 1.4. And this is really an important discovery, that we can actually do this and get much higher efficiencies in our process using the system. So this is over 29 cycles, it's fairly constant. The utilization capacity is about 1.43. The minimum energy is pretty low. The actual average energy is about 64 kilojoules per mole. I know we can do a lot better than that. Well, I hope we can do a lot better than that with the refinement of this whole process. So that's right. So I just wanted to leave you with that. I've got another half hour. No, I'm just kidding. I could talk about how would you actually apply these in a real engineering type system. This is one of the ideas we would have. A lot of people, what they do, they'll absorb the CO2 on absorbent beds, and just one absorbent bed, and then they'd use the same absorbent bed that they'll heat it up and release the CO2. So you've got a very large volumes here that have to be heated and cooled each time. Our idea is, if we can take these electrochemically activated type systems, what we can do is activate it and send it through a hollow fiber modules, as shown here. Send it through the lumens of hollow fibers and have the air blowing over the fibers. We can then capture CO2 from the air. And then the actual solution gets saturated with CO2, and we can then take that and take it to electrochemical cell again, where we can regenerate that sorbent and release the CO2 as a pure CO2 stream. The nice part about that is that we can do this release at pressure, and the actual unit for it would be very, very small relative to the actual units that used for capture. For instance, we take air here on the order of say 0.042%. And we can actually get the CO2 up here on the order of molar type structures, maybe. So this unit here can be very, very small, and it can be quite efficient in terms of the CO2 release type process. And that's something we are working towards now. So I want to leave you then with with the conclusions that there is I think, a very strong role for electrochemically modulated CO2 capture type systems. These electro-swing technologies can play a role. We can think about, because they're isothermal, there are no external heat sources in these systems, which is good. It can be plug-and-play operation. It can be easily installed. I think it's an important consideration. They modulate, can be easily scaled up or scaled out, scaled down as needed, depending on your applications. They have favorable energetics on the order of 1 to 4 gigajoules per ton of CO2 captured. That's a pretty good, favorable, and they can use non-carbon energy sources. These are applicable across multiple scales and concentrations. We can think about power generation, large-scale power plants. We can think of various industrial sources, such as the steel, cement industries, which have a very large CO2 footprints. They can be used for mobile sources if we want. They can be used on trucks. They can be used ships. Can be used on trains and cars, if need be. They can be used in indoor environments for modulating the CO2 in a room like this, so everybody goes to go to sleep. And avoid the number of air exchanges that you need in the system, so you can sort of minimize the energetic costs associated with heating and cooling as you exchange air with the outside environment. They can be used for direct air capture, and I haven't talked about it. We can also use similar kind of concepts, not exactly the same concepts, but also electrochemical modulation of the pH of ocean water to release CO2 as well. There are, of course, many engineering challenges, there always are. You have to worry about bubbles in these electrochemical cells. When you start releasing the CO2, they form bubbles. They can really impede the overall efficiency of the systems. You do need to be worried about sensitivity to oxygen and other interfering species. I talked about oxygen. There could be things like NOx and SOx and things like that. And how do we actually couple with renewable resources? If you start thinking about solar energy, for instance, solar power, you're talking about tens and tens of acres of solar panels for, say, a 500 kiloton CO2 capture per year. So there are some big issues associated with that as well. But I just want to leave you with a couple of points. One is, how much energy is this going to take? This is from a review article that we put together a few years ago. Mim Rahimi was a postdoc of mine. And this is the electricity generation in petawatt hours that's being projected over the next 3 decades or so. And you can see it's going up and up. If we wanted to convert all the CO2 to chemicals, we'd need about this amount of the energy, total energy that's around, okay? If you want to look at electricity for carbon capture and storage, this is basically what we would have under the different scenarios, depending on how much CO2 you want to capture each decade. And this is starting out a small amount now, but you're getting up to on the order of 10 gigatons per year. It would have to be done. And you're talking about the order of 2 to 3 petawatt hours in this particular case. So if you look at the total stuff here, you're talking about the order of about a few percentage of the electricity that's going to be generated will have to go towards doing the capture, if you want to use all electrochemically based capture systems. Just something to think about. Okay, the question is, what's captured CO2? Now what do we do with it? Okay. Basically, we can think of different things. You've got the fossil fuels, biomass, all these different sources for the CO2. We get the CO2, we presume we've done a good job in getting that out. That can then be used for direct use, either in greenhouses and so on. We can use them as solvents for dry cleaning, enhanced oil recovery, and the like. They can be used heat transfer fluids and refrigeration and so on, and also food and beverages, welding, medical uses, very small scale device utilization. On the other hand, you can actually think about conversion. We can convert this to fuels, to chemicals and building materials. And there's a lot of nice work going on in these general areas, some of it here in Reno. So, but if you think about the total capacity, how much can you really absorb? If you take all the CO2 and if you want to build or make these chemicals and things like that, how much of the CO2 are you actually going to use before you saturate the market? It's a small amount, actually. It's not going to be a large amount. These are very important that we focus on this, but it is not, I hate to say, it's not going to solve the CO2 problem. We are going to have to think about what we do with the rest of the CO2 that we can't do anything with. And this is when it gets buried in in deep saline formations, old oil and gas reservoirs. It can also be biochar or basalt and things like that. It's a whole range of different things. And that's going to be something else, another whole story that we can talk about there. So with that, I'd like to finish up, and I'd like to acknowledge the students that have worked in this, students and postdocs that have worked on this. This is the email process I discussed. I've got a couple of other people I should add on this right now, but we didn't talk about the ocean capture work, but these are people, some of the people who have worked on the redox systems over the last few years. And of course, my various funding sources as shown here. So with that, I'd like to thank you for your attention, and I'll be happy to answer any questions you may have.